Hello everyone, and welcome to this video titled Derivatives and the Shape of a Graph. This is part 2 on concavity and points of inflection. So in this video, I'm going to be going through a preview version of a Knewton Alta Homework Assignment, also titled Derivatives and the Shape of a Graph, but I'm specifically going through the objectives that are under the heading Concavity and Points of Inflection. So please understand that this is a preview version of this assignment. So the questions I work on in this video may not be the exact same questions you see when you work on it as a student, but the objectives should be the same, and the methods I use should be similar to what you should be using to solve similar problems. All right, so here we are at Knewton Alta's site. And this is a preview of what in this course I'm teaching is section 4.5 on derivatives and the shape of a graph. In the upper right hand corner, you should see a mastery bar that tells you how far along you've gotten in an assignment. Next to that, an activity log. So again, this assignment has many objectives. Looks like 9 objectives. The part 1 of this I did was on the first derivative test objectives. So I have begun for this video the concavity and points of inflection objectives. So there's only 2 of them I'm going to be working on in this video. And then part 3, I'll be working on the 3 objectives from the second derivative test. All right, then back on the main screen, you should see a current objective. Beneath that, a question related to that particular objective. And at the bottom of every question, you should be able to find a feedback button. So if you see any problems with the question itself or with the answer explanations after the question, you can send feedback directly to Knewton support, and hopefully someone will get back to you relatively quickly with a way to fix your issues. I hope it's understandable that you will not have the instructor cheat button, right? That's for instructors only to fill in correct answers. I'm not going to be using that in this video because you won't have it either. But then you should also be able to find a more instruction feature. If you're working on an objective and don't remember what to do or don't remember the material very well, you can click down here on more instruction and it'll give you some reading to do or videos to watch or both related to that particular objective. And hopefully reading through that stuff and working on that will help you work through those assignment problems. All right. So before I get into the actual questions, I would like to talk about, concavity and points of inflection. And we'll get into the questions after. So in part 1 of this assignment, we talked about what the first derivative told us about a function. And the first derivative test for locating local maximum values and local minimum values, right? Tops of hills and bottoms of valleys on the graph of a function. So here we're going to be talking about what the second derivative tells us. Right, so given a function, just say some function of x, y equals, some function f of x, that is twice differentiable, meaning that it has a first derivative and second derivative function that we can find. I'm not going to write that. So remember the second derivative which would be, f double prime of x, or that, d squared y, or f over dx squared, right, with the Leibniz notation, or just y double prime, whatever. All three of these, mean the same thing, the second derivative. The second derivative will help you indicate what's called the concavity of the graph of the original function. So the concavity of the graph of y equals f. Right? All the conclusions we make will be about the original f function. Now, concavity, the concavity of a curve, this is pretty much just which way the graph is curving. So you got two possibilities here. You got, a graph could be concave up. So a piece of curve that would be concave up would look like this, like a smile. Something that if you were, it's curling upward, it would hold water. If you imagine this as a bowl holding water, that would be a piece of curve that's concave up. And of course, the other way would be where we're going to try to figure out where is a curve concave down. So this, kind of flip this over. You're on a piece of curve that's curling downward like this, right? If you imagine it being a bowl, it's a bowl that's dumping water. Now, if you look at how do we use the second derivative to tell us where a piece of curve is concave up or concave down, take a look at points on a piece of curve like this. So let me look at this one here that's concave up. So if you take a look at the points on this from left to right, and look at their tangents, which direction the curve is going in. You see over on this side of the curve, the value of the derivative f prime. So remember f prime, the first derivative, told me the slopes of tangents. So over here on this piece of curve, my f prime, the first derivative, is negative. And then if I keep curling up like this, concave up, at some point, we're at the bottom of some valley here, where f prime would be 0. I have a horizontal tangent line. And then on the right side of the curve here, my tangent lines have a positive slope, so f prime is positive. So on a piece of curve, on a piece of the graph that's concave up, the value of the derivative, the first derivative, would be increasing, right? Going from negative to 0 to positive here. So on a piece of curve that's concave up, f prime, the value of f prime is going up, is increasing. So that means the second derivative must be positive. Because remember what the derivative of a function tells us, right? Remember when the first derivative was positive, the original was increasing? So again, wherever some expression is increasing, its derivative will be positive. So on a piece of curve that's concave up, again, f prime, the first derivative is increasing, so its derivative, f double prime, will be positive, will be greater than 0. And then a very similar fashion on these pieces of curve that are concave down, curling down like this. If you take a look at points on a piece of curve like this as you go from left to right, See on the left side of it, you got f prime is positive, right? The first derivative is some positive value. These have positive sloped tangents. Then at some point, you'd have a horizontal tangent line, and this on a piece of curve like this, rounded down, curling down, concave down. And then at these points over here on the right side, the value of f prime would be negative, right? Negative slope tangents. So as I go from left to right on a piece of curve like this, going from positive slopes to negative slopes, so the value of f prime is going down, right? The value of the first derivative is decreasing. And as we talked about with the original function in the first derivative, right, wherever a function is decreasing, its derivative is negative, right? So if the first derivative is decreasing from left to right here on a piece of curve that's concave down, then its derivative, so f double prime, will be negative. Okay, so that's how we're going to determine, using the second derivative, where a function is concave up, curling up. It's where its second derivative is positive. And then where a function is concave down or curling down like this, it's where the second derivative is negative. All right, so again, the first derivative of a function tells you where it's increasing or decreasing, going up or down. And the second derivative of a function tells you which way it's curling, if it's curling up or curling down, concave up, concave down. All right. So now these two cases are where you have a positive second derivative, negative second derivative. But then there's still two other possibilities where is the second derivative, zero or undefined. And those are going to be once again called critical points. But they're critical points for the second derivative. So critical points or critical values, this is where the second derivative, so f double prime equals 0, or where the second derivative, I'll just say dne for does not exist or is undefined, right? So points where this happens, that's still in the domain of the original function, right? You gotta actually talk about having points, are called critical points. So some examples of things like this, maybe a graph is concave up, so the second derivative is positive, and then at some point it becomes concave down, right? Curls up, hits a point, curls down. So again, on a piece of curve like this, the second derivative would be positive, and then on a piece of curve like this, second derivative would be negative, right? Curling down. So at a point where that changes like this, nice and smoothly, that'll be a place where the second derivative, is 0. Now, this changing concavity doesn't always happen. I mean, I could have a piece of curve that's curling up, and then you hit a point, and then suddenly it's also, curling up again afterwards. Now, this is one of them pointy places. So again, here's a point where second derivative would be, on this piece of curve, second derivative positive. Same thing for on this piece of curve, again, curling up, concave up, concave up. But then you see at this point here, where there's this sudden change in direction, right? A sudden shift in direction, a pointy place, a sharp place. That's where the function's derivatives don't exist. So that my second derivative here would be non-existent, right? It would be undefined. Right? I could have another one like that where maybe it's curling up, hit a point, and then just, again, sudden change of direction starts curling down. Again, same thing. Here's a piece of curve where the second derivative. I mean, there's other possibilities. I'm only drawing a few of them here. But there's one piece of curve where the concave up. Here's a piece of curve where it's concave down, so the second derivative is less than 0. And then once again, at these sharp points, these pointy places where there's a sudden change in direction, that's where your derivatives don't exist, right? So second derivative, say dne there. Whatever. And again, this isn't the only 3 options. There's other pictures you could draw. Concave down, then concave up, or concave down, then down again, or down, then up again, whatever. Right? So I'm not drawing every possible option here. Now, at these critical points, right, the points where the second derivative is 0 or undefined, you could get, that doesn't happen here, but like in this first and third picture, you could get a change in concavity. See how this is concave up on the left of that point, and then concave down to the right? Same thing at this point in the third picture, it's concave up on the left side, but concave down on the right side. So points where concavity changes are these things called inflection points. So points where concavity changes sign. So the value of the second derivative changes sign, goes from positive to negative or negative to positive. That's where we're going to have these things called inflection points. Again, points where concavity changes. So another way to think about that is the second derivative, f double prime, changes sign, sign, right? Goes from positive to negative or negative to positive around that point. Points where concavity changes, f double prime changes sign, are going to be called inflection points. All right, so again, some sample pictures. Here's the first picture I had up there. That would be considered an inflection point, a point of inflection. Again, you have a positive second derivative concave up on the left, negative second derivative concave down on the right. Here's another one where maybe it's concave down on the left and then concave up on the right. So there's another picture where that would be considered an inflection point. And then the picture I had here, where it's concave up, then you hit a point and then concave up again, that's not an inflection point. Even though it's a critical point, right? The second derivative wouldn't exist at a place like this. This would not be considered an inflection point. The reason is the first derivative, the second derivative, it's concave up, positive, second derivative on the left, concave up, so positive on the right. So on both sides of this point, you have the same sign of the second derivative. It doesn't change sign. This point here in this picture would be an inflection point. So this, instead of drawing it again, this would be an inflection point. Because at the, to the left it's concave up, to the right it's concave down. The second derivative changes sign. The graph changes concavity. Right, but the key is to finding these places though, right? These inflection points, right? These inflection points can only occur at critical values, where the second derivative is 0 or where the second derivative is undefined. So we find these critical values and then we Just like with our first derivative, right? We find these critical values and then plug in, values around these to see where concavity changes, to see where the second derivative goes from positive to negative or negative to positive. Right. So back to our questions, right? Now that I've at least, brought out what these things are, how to determine concavity, and find inflection points, right? So that's this first objective I'm looking at here. Find inflection points and intervals of concavity given a function. So here we're asked to consider the function f of x below, right? Some polynomial function here. And the question is, at what value or values, maybe more than one, of x are the inflection points? So they don't even ask for the actual points themselves. They don't ask for the y coordinates of the points. They just want the x coordinates of the points of inflection. And I'll go to Desmos too. We'll punch this in Desmos and see the graph there, and take a look at where if what I say are my inflection locations are actually places where you have inflection, a change in concavity. So enter answer using exact values, right? So don't punch anything in, don't round to so many decimal places or something like that. And separate multiple answers with a comma if necessary, right? So if there's more than one, I'm going to separate them with commas in this little box here. Okay. So here is the function we're given. Some polynomial function, f of x equals 5x to the fifth minus 6x cubed plus 10x and then minus 5, right? And we're asked for where are the inflection points going to be, right? At what values of x? So to talk about inflection points and changes in concavity, you need to get down to the second derivative, right? So you need to do the first derivative first, right? So first derivative, this power rule term by term here, simple polynomial function would be 25x to the fourth minus 18x squared and plus 10. There's your first derivative. And then second derivative, right, f double prime. And just a simple power rule term by term here would be 100 x cubed minus 36x. And that's it. And if I want to make it easier to state where the critical points are, we could factor this a little bit. Both of these have 4x in common. 4 goes into 136 evenly, and they both have at least x to the first. And if I were to factor out 4x, what would be left over would be 25x squared, then minus 9, right? 4x times 9 would be 36x, and then this here even is a difference of squares. So we got 4 times x, and then this is 5x minus 3, right? 5x squared minus 3 squared. So this will factor to 5x minus 3 times 5x plus 3. Okay, so then so looking at it in factored form, I hope it's obvious. It's easy to find the critical values, critical points. So once again, these critical points are where is the second derivative equal to 0, or where is the second derivative undefined. Now, being that this is a polynomial function here, it's not going to be undefined anywhere, so I don't have to worry about that part. So now I'm just solving this, where is this equal to 0? Now in factored form here, it makes it real nice and simple. Just writing the factored form of the second derivative. And again, I hope it's clear when it's in factored form that this happens when x equals, 0. right? Because x is one factor. When x equals positive 3/5 would make this middle factor 0, the 5x minus 3. And when x equals negative 3/5, right, that makes the 5x plus 3 factor 0. Now, these aren't going to be all these might be my answers, but I mentioned before, just because you have a critical value, that doesn't mean there's going to be an inflection point. All right, you also have to show that the concavity will change, the way it curves will change at these values. So we look at where is the second derivative positive, where is the second derivative negative. So like with the first derivative, I'm going to go make a number line here. Okay, so here's all the values in the domain of f. All right, now this is a polynomial function, so I can use any value of x I wish. So the domain's all real numbers, and then I'm going to see what happens to the value of the second derivative, right? So be careful to label these things, right? This is going to be a number line for the second derivative values of f double prime. So I mark off where the second derivative is 0, so at x equals 0, positive 3/5, and negative 3/5. And I'll say, hey, the second derivative is 0 and 0 and 0 at these values. And then these critical values, right, they break the number line up into so many intervals, right? This is 4 intervals here. There's to the left of negative 3/5, between negative 3/5 and 0, between 0 and 3/5, and to the right of 3/5. So now I just plug in representative values from each and see if the second derivative is positive or negative. Now again, I think it'd be easy to look at this in the factored form. If I plug in a number that's big negative, say -1, -1,000,000, right? Something to the left of negative 3/5. We'll have, clearly this first term in the non-factored form will be a giant negative number. So we get a negative value for the second derivative there. And then all these, if you remember your polynomial function stuff from pre-calculus, all these intercepts, all these critical values here have a multiplicity of 1, right? X to the first, 5x minus 3 to the first, 5x plus 3 to the first. So it will change sign at all these zeros. Now you can double check this by plugging in values in here. Plug in, say, -3/10, +3/10, or something between 0 and 3/5. Plug in, something bigger than 3/5 into our second derivative here and see that you got positive second derivative, negative second derivative, positive second derivative. Now I'm going to, like we did with the first derivative, underneath here, I'll say what's happening on the graph of f. Remember, the value of the second derivative will tell you what's happening on the graph of the original function. So in this interval here, so from -∞ up to -3/5, f is going to be concave down. I'll just put this little down curl here, right? You got negative second derivatives, so f's going to be concave down. Then between -3/5 and 0, there would be a positive second derivative, so f is going to be concave up. And then between 0 and 3/5, got negative second derivative, so f's going to be concave down. And then positive second derivative to the right of 3/5, so from 3/5 onward, f's going to be concave up. Now, there's going to be problems coming up where you have to state all this. So I'll do that here. We can say that f, right, the graph of the original function will be, concave up on the following intervals. So again, concave up, curling up, wherever the second derivative is positive. So from -3/5 to 0, union, right, because there's another one, and then 3/5 to infinity. And then we can say f will be concave down curling downward on the following intervals. Just look where the second derivative is negative, and that's from negative infinity up to negative 3/5. And then there's more, so in union with, and then from 0 to 3/5, you got a negative second derivative, so concave down. But you see how the value of the second derivative does change at every single one of these. So since the value of the second derivative changes, the concavity changes at all these points. These are points of inflection. These are where you're going to have inflection points at all these, at negative 3/5, at 0 and 3/5. Now, if I wanted to know exactly what the points were, plug them back into F, plug negative 3/5 into F, plug 0 into F, you get -5, 0, -5, that's an easy one. And then I plug 3/5 into F, and you can get the points. Now, we'll see what those points are in Desmos, right, just to double check. So I'm going to go to my Desmos calculator here and put the function they gave us in. So this was, 5x to the 5th minus 6x cubed plus 10x minus 5. And now the thing about Desmos is it highlights intercepts, right? Here's the x-intercept, here's the y-intercept. I'm going to put in those inflection points, right? It doesn't really highlight those. So negative 3/5, comma, and then f of negative 3/5. All right, just because I labeled the function f earlier. So let's label that. So that's this point down here. Now, if you zoom in, I know it looks pretty straight. It's not that curvy. It's a pretty straight line. But you see how to the left, it's kind of curling downward. All right, it's almost like part of a bowl opening down. You got concave down. But then at this negative 3/5 point, it changes to curling upward slightly. All right, this is part of a bowl that's opening up, part of a bowl holding water. Up until 0, -5 here, right? So from negative 3/5, the point with x equals negative 3/5, up to the point where x equals 0, see it's concave up. But then after this point, it's, concave down again. Right? It's not now from 0, -5, you're concave down to the right of that. It's curling downward up until the point where x equals positive 3/5. So 3/5, comma, f of 3/5. I'll label this point as well. You see between 0, -5 and this point here, it's against very, very slight, but it is part of a curve that's curling downward, concave downward, negative second derivative. And then from this point onward, from this point where x equals positive 3/5 onward, it's curling back up. It's part of a bowl holding water, concave up. And again, it's very, very slight. Maybe not so easy to tell with this picture, but that is happening in our graph. Now, what we're going to enter in the assignment, and all they don't want the actual points themselves, right? They don't want the outputs. They just want what the x values are for these inflection points. So that was negative 3/5, comma, one was at x equals 0, comma, and one was at x equals positive 3/5. All three of those had an inflection point at them. All right, then when you submit, it'll tell you if you got something correct or incorrect and give you some sort of answer explanation. I would highly recommend reading through the answer explanations, whether you got it right or wrong. If you got it right, perhaps you did it in a very inefficient way. And reading through the answer explanations, you see that they're doing it in a much faster way, much more efficient way that you like better and would want to try for future questions that are similar. Definitely read through these if you got it wrong, though. All right, hopefully you can read through and understand where you went wrong and learn from your mistakes for future questions of that nature. right, so moving on. All right, so they switched up. Again, there's only the two objectives in the heading I'm working on, right? So they switched us to this other one, the understand the relationship between the graph of a function and the sign of its second derivative. And I've said that already, right? Wherever the second derivative is positive, the original function will be, concave up, curling upward, part of a bowl that holds water. And if wherever the second derivative is negative, that's where the original function will be concave down or curling downward, or part of a bowl that's dumping water. I don't know how else you want to think about that. So here, we're given the graph of a function, right? The graph of f is given below. On what intervals is the second derivative, right? F double prime negative, and give your answer in interval notation. Use commas to separate multiple intervals if necessary. So look, they highlight these points where the concavity changes to help you. So you see this point here at -3, 0. To the left of that, you're part of a bowl holding water, right? That is definitely concave up. So from -infinity up to -3, the value of the second derivative would be positive. But they want to know where it's, negative. So that's not one of my answers. And then from this point here to this point here, so from -3, 0 to 0, 2, see now it's changed concavity. The way it's curling is curling downward. This piece of curve is part of a bowl that would be dumping water. So the value of the second derivative would be negative from -3 to 0, right? Your intervals on the x-axis. And then to the right of this point 0, 2, to the right of 0, we're back to a holding water, right? We're back to concave up, positive second derivative. So looking at this picture, the only piece of this graph that's concave down are from x values of -3 to x values 0. So the interval from -3 to 0 is the only interval I'm entering here. All right, and there's no other one, so I'm not going to put a comma and have a second interval. Okay, so pretty simple there when you're given the picture of a graph. And of course, they highlight, these points of inflection for you as well. That's also very nice of them. All right, so another one similar to this. Now be careful. This is the other way around, right? This is the graph of the second derivative is given. So this is not the graph of f, not the graph of the original. This is the graph of the second derivative function, the graph of f double prime. So on what interval or intervals would the original graph, right, would f be concave up? And, interval notation, use commas to separate multiple intervals. So again, where the original function would be concave up is where the second derivative has positive value. So if you look here, you see to the left of -3, the second derivative is below the x-axis, has negative value. So not up to -3. Now between -3 and 1, now the second derivative, this f double prime graph, has positive value. So if I were to look at the graph of the original, it would be concave up between x equals -3 and x equals 1. And then concave down again between 1 and 3, is again between 1 and 3, the value of this second derivative is negative. And then to the right of 3, from 3 to infinity, the value of the second derivative is positive again. So the graph of the original would be concave up on this interval. So there are two places, two intervals where the original curve, where the graph of f would be concave up, and that's where this second derivative has positive values. So for between -3 and 1, and then from 3 onward. So intervals where f would be concave up, the interval from -3 to 1, and then again they're saying separate the intervals with commas, and then the interval from 3 to infinity. And always, parentheses on these infinities. So you're just, again, real quick at paying attention to where is the value of the second derivative positive. That's where the original will be concave up. And where is the value of the second derivative negative? That's where the original will be concave down. All right, so now back to, it's another polynomial function. So we're given some polynomial function, and once again asked to state what values of x will there be inflection points. So again, they don't want the outputs, they don't want the y coordinates of the inflection points, just what are the x coordinates of the inflection points if it has any. So pretty similar to the first question we had in this objective, right? It's another degree 5 polynomial function. All right, so here we're given f of x equals -5 times x to the 5th plus 3x to the 4th, then plus 7x plus 2. Again, since we're asked about points of inflection, that involves a change in concavity, we need to go to the second derivative, right? We need second derivative information to answer this question. So the first derivative would be -25x to the 4th plus 12x to the 3rd plus 7. And then the second derivative would be -100x to the 3rd plus 36. So again, very, very similar, just with different coefficients here. This, that's negative and this is positive now. X squared. And okay, so again, factoring this is, they both outpull a -4 because the lead is negative here. -4 times, now this is x squared in common. So yeah, this will be a little different than the last problem, because this now has a, this will be x equals 0 as an x-intercept with a multiplicity of 2. So see how that affects the sign changes. Now if I pull out -4x squared, then the other factor would be 25x, then -9. Right, so again, a little different because of the different powers here, but still like the coefficients of 136, kind of similar. So anyway, the critical points. I said earlier, right, you got to find where the second derivative is 0 or where the second derivative is undefined. Once again, this is a polynomial function, so don't have to worry about the undefined part, right? It's polynomials and all its derivatives are defined everywhere. All right, so you can probably tell, I'm not going to write this again. This is going to be 0 if you look at factored form. When x equals 0, all right, that'll make the x squared factor 0. And then 9/25. Then I'll make a number line for the second derivative, right? So here's the, imagine the x-axis, and we're seeing what's the value of f double prime now at 0 and 9/25. The value of the second derivative is 0. And then you plug in values around this. Now plug in any big negative number here. And that'll plug in -1 million, -1 billion, right? This first term dominates up here back in non-factored form for the second derivative. This will be a positive value. right? Or take again, -1, -2. Right, this would be a so no matter what you plug in here, this is going to be a negative, or if you look in factored form, right? No matter what you plug in over here, this will be a negative factor. And you got -4 making positive, and then again, x squared will be positive no matter what, because it's squared, even power. So yeah, you have positive second derivatives to the left of 0, but then also between 0 and 9/25. And that's because of this whole x equals 0 having an even multiplicity. So you're going to have a positive value in here too. And try it, plug in some value less than 9/25, but still is a positive number. This will be a negative, right? This will still be a negative factor here. This 25x minus 9, and then negative and positive, it'll be positive all around, all told. And then something bigger than 9/25. Now, the multiplicity of 9/25 is 1, so it will switch signs there. And you can, again, plug in some huge positive number, and you see the lead term is negative up here, big negative. So it's a negative value for the second derivative. So the function f, right, the original graph will be concave up to the left of 0. It'll be concave up still to the right of 0. Concave up to the left of 9/25, and concave down to the right of 9/25. So there's only one place where there's an inflection point. There's only one value of x where the concavity changes, and that's at this 9/25. So that's going to be my only answer. Now let's actually verify this, right? Let's go to Desmos, take a look. So again, back here now, I don't have the y coordinates of the inflection points, but we can have Desmos show them for us. So -5x to the 5th plus 3x to the 4th plus 7x plus 2. So there's the graph. Now, I mentioned, the point at x equals 0, which would be 0, 2. Remember, I said this would not be an inflection point. So look, see how to the left it's concave up, and then it's still on a piece of curve that's concave up. Right? It doesn't change concavity until 9/25. So here's the point with 9/25, 0.36, and then f of, oh, let's put 0.36, right? So that red point there. So see, it doesn't change concavity. So see how it's concave up to the left of 0, 2. Then also a little bit here. It's still on a piece that's concave up to the right of 0, 2. But then as soon as you hit this point here at 0.36, to the right of that, then you're on this piece of bowl dumping water, right? You're holding water to the left of this point, and then you're dumping water, concave down to the right of it. And that's what our number line stated. But there's only the one inflection point here at positive 9/25. So that's what I'm putting here. Just 9/25. It's the only one. Again, even though the second derivative was 0 at 0, x equals 0, it didn't change sign. It didn't change concavity there, right? The places where you have inflection points are where it changes. All right. All right, so back to this one where you're given a graph. All right, so look, this is the graph of f prime, not f or f double prime. Now, pointed this out in the discussion at the opening of the video. Wherever f prime is increasing, so where the graph of f prime is going up, that's where the second derivative will be positive, and where the original graph will be concave up. And then wherever f prime is decreasing, right, wherever f prime is going down, that's where the second derivative will be negative and where f will be concave down. Okay, so if we're given the graph of f prime and asked where is the original function concave down, I need to figure out where is f prime decreasing. Because if f prime is decreasing, then f double prime will be negative and the original will be, concave down. So look at this graph here. Now they point out that some nice points for us. So again, this is the graph of f prime. So wherever this is decreasing as you go from left to right, that's where the second derivative will be negative and the original thing will be concave down. So from negative infinity up to -4. F prime, right? F prime is increasing. So the graph will be concave up on that interval. Now from -4 to 0, that's an interval where f prime is going down, right? The value of f prime is decreasing. So again, f prime is decreasing, meaning f double prime will be negative and f will be concave down. So this is one interval from -4 to 0. Then from 0 to 4, f prime, this f prime output is increasing. So f will be concave up. And then from 4 onward, right, from 4 to infinity, f prime here is decreasing. So great. That means f will be concave down. So again, wherever f prime is going down, that's where your function will be concave down. So from -4 to 0 is one interval, and then looks like from 4 onward, 4 to infinity, the other one. So intervals, f is concave down over the intervals from -4 to 0. And again, I think they said separate with commas. Yeah, commas to separate multiple intervals. And then from +4, to infinity for the other one. All right, great. So another graph one. Now this is like the second problem we saw in this objective. So this is the graph of f double prime. This is the graph of the second derivative. And we're asked about, where is the original f going to be concave down? So remember the second derivative, wherever that's negative, wherever that has a negative value, that's where the original graph will be concave down. So from -3 to +1, right, the second derivative here has a negative value. So the graph of the original will be concave down over that interval from -3 to +1. And then from 5 to infinity, right, 5 onward, this second derivative graph has negative values. Okay, so the original graph will be concave down. So -3 to 1 and also 5 to infinity are my answers here. Interval from -3 to 1, comma, interval from 5 to infinity. All right, so that objective's done. So now the rest of the problems I'm doing in this are just to finish up that other objective in this heading on the concavity and points of inflection, right? So I'm just going to be finishing this one up here in this video. And again, I mentioned this at the beginning, the second derivative test will be in another video, those three objectives, part 3. Right? So so once again, we're given some degree 5 polynomial function, asked to find, now this is a little different. They're not asking us for the x values of the points of inflection. They're just asking us for over what intervals is the function concave up. So I'm going to go to find the second derivative, make my little, find the critical points. Where is the derivative? Where is the second derivative 0? Where is it undefined? Which for polynomials, it will never be undefined. Make a number line, plug in values, think about the values of the second derivative for different intervals of x. And we're looking for where the second derivative is positive, right? That's where the function will be concave up. So here we're given another fifth degree polynomial. 6x to the 5th plus x to the 4th minus 5x minus 6. And we're asked about concavity, right? Where is the function, this function, the graph of this thing? Concave up. To answer such questions, go to the second derivative. So the first derivative would be 30x to the 4th plus 4x cubed minus 5. And then the second derivative is what I want to get to. So 120x cubed plus 12x squared. And make it nice and easy on myself. I see how we can easily factor this, right? You can they both have a common factor of 12x squared. And if I pull out a 12x squared from each of these, the other factor would be 10x plus 1. So my critical values in this second derivative will be 0 at x equals 0, right? Because the one factor is x squared here. Clearly, if x were 0, this would be 0. And at x equals negative 1/10. That makes this 10x plus 1 factor 0. Make a number line for the second derivative, right? This is, I'm labeling this f double prime. Now at x equals 0, the value of the second derivative is 0. And then at x equals, negative 1/10, the value of the second derivative 0. And knowing, again, this second derivative is a cubic with a positively coefficient. Knowing what you should know about polynomial functions, this will be happening. You'll have negative values to the left. The second derivative should be negative to the left of negative 1/10. The multiplicity of negative 1/10 is 1, so it's going to change sign there. Be positive second derivatives between negative 1/10 and 0. And then 0 has an even multiplicity, multiplicity 2, so it's not going to change sign at those even ones. So still positive second derivative. So we got two intervals where the second derivative is positive. F is going to be concave down for the negative infinity to negative 1/10. F is concave up from negative 1/10 to 0, and then concave up again from 0 to, infinity. Now, I wonder if they connect these. I'm going to put the two intervals where the second derivative is positive, but because they're connected, there's no change here. They might put them together. Let's just see what happens. So I'm going to put these two intervals, right? So f is concave up from negative 1/10 to 0. So again, interval concave up where the second derivative is positive. That's from negative 1/10, up to 0, and then it's not positive there, right? So now it says give your answer in interval notation. Didn't say anything about commas, so I'm going to do the union symbol now. All right, and then this 0 to infinity. Infinity is in the basic keyboard. All right, from negative 1/10 to 0, between those values, second derivative is positive, so concave up. And then from 0 to beyond 0, 0 to infinity, for those values, second derivative is positive, concave up. All right, so they must connect them because there was no change. Okay, so they must connect them. So since there was no change here, where there's no change in concavity at 0, it's concave up this entire time, right? This is curling up the whole time from negative 1/10 to infinity. So I'll just change this up, put it all together, make it negative 1/10 to infinity. Yeah, so they connect them when there's no change. On a test or something, if I was to test you on this would be perfectly valid up here for me. It still tells me, you understand where the second derivative is positive. That's where your curve is, concave up. So they go through all that here, and I'm sure that, so they must explain because, so, yeah, okay, see, since it's continuous at 0, they can combine the intervals. All right, and so again, notice this isn't wrong. This is not wrong. I know it said it was wrong earlier, but because it's continuous, they will put them together if there's no change. And it says be aware of that. All right, so another one. So again, we're asked for intervals where the function's concave up. So just be aware that, this is probably going to be my last problem here. It looks like I'm getting near the end of the activity, filling in this objective. Just understand that, you might see some problems where they ask you where it's concave down. So just remember that's where the second derivative is negative. All right. All right, so now we're given some, degree 4 polynomial function. So f of x equals 7x to the 4th minus 4x squared minus 8x minus 5. And again, asked about concavity. Where is this thing going to be concave up? Again, they could ask about concave down as well, but so you're talking concavity, you got to go to the second derivative, right? So the first derivative would be 28x cubed minus 8x minus 8. And then the second derivative be, let's see, 60 and 24. So 84x squared, then just minus 8. And I'll factor some stuff out of here, right? These both have 4 in common. So I'll pull a 4 out, and then we'd have 21, 84x squared minus 2. And this is going to be, so I'm doing my critical values over here now, right? So this is going to be equal to 0 at 2 different places. X equals positive square root of 2/21, and x equals negative square root of 2/21. 2 over 21, that's 2 over 21. Because we have to add 2, divide by 21, do plus or minus square root. Right? And if you look at your number line for the second derivative, right, x, and then this is for f double prime, and this is equal to 0 at negative square root of 2/21 and positive square root of 2/21. And then once again, knowing what you should know about polynomials, this is a degree 2 polynomial, the second derivative here. So if you were to graph it, it would look like a parabola with a positively coefficient. So it would have positive values to the left of this 0, negative values between the zeros, and then positive to the right. Or it'd be like a parabola shape opening up, going up to the end on left end and right end forever. So our original function is concave up to the left of negative, from negative infinity up to this negative square root of 2/21 value. Then it's concave down, f is concave down between the two, and then concave up again to the right. So f is concave up. So here's what I'm going to be entering. And they're not connected this time, right? So you saw in the last example, if they're connected, you connect them because of the whole fact that polynomials are continuous. So concave up on the following intervals, right? From negative infinity to this negative square root of 2/21 value, union, and then this total, so I'll need the union symbol here because it's totally separate, right? There is a gap between them. Positive square root of 2/21, to infinity, right? So entering those where the second derivative is positive. So in parentheses from negative and infinity is in the basic keyboard, comma, up to that negative square root of 2/21. Right, you don't have to rationalize. Let's leave it that way. And then the union symbol is back on the sets keyboard, right, union. And then from positive square root of 2/21, I'm back to the basic keyboard for square root here. And positive square root of 2/21 to infinity. And that should be good. I think they just said interval notation, right? No commas, so I need the union symbol here. Right. All right, so that's it for this video. Again, I just wanted to go over some problems from the objectives. So you see they rationalize the denominator, square root of 42 over 21. But I just wanted to go over the objectives that were, in this concavity and points of inflection section. So hopefully watching me go through these problems here help you out when you're working on them yourself. And thank you very much for watching.